All right. So, the two functions they give us are the first derivative. In other words, you've done a lot of problems where x is moving along the, or a particle is moving along the x-axis.
Yeah.
And, you know, you have to figure out its velocity, its acceleration, its position at certain times. Position function, first derivative of that is velocity, second derivative of that is acceleration.
Right.
Okay. So I think I have a handle on this. If find the acceleration vector of the rover at time 1. Well, it's been a while since I've dealt with this, and I'm not even positive this is correct. Maybe you can let me know. I am going to take the first derivative of these first derivatives.
Okay.
In other words, to get x double prime.
Right.
And in fact, let me do it here. Let me start writing on this thing. And again, I'm not 100% sure about this, but so we've got x double prime of t equals what?
X double prime of t equals negative 24 cosine 2t squared.
Almost. No. I think it's 12 going to be times 4.
4t.
So it should be minus 48, I think.
Yeah, it'll be minus 48t because that's the derivative on the inside.
Right. Times cosine of 2t squared. Yeah. And now, and y double prime.
Y double prime of t equals
Go ahead and do it just piece by piece. In other words, when I do these, I find them much easier to do if I don't try to figure out what the coefficient is. In other words, I do not start at minus 48. I start at minus 12 sine of 2t or cosine of 2t squared times 4t. And then I simplify it. And
okay, so
I think that's actually an easier way to actually mechanically do the derivative. So let's start with 10. Is it going to be sine or cosine?
It'll be negative sign, right?
Okay, so let's put the negative in front of the 10.
Then times 1 plus root t.
Write it like that. Might as well get rid of that radical sign. Times what?
Times 1/2 t to the negative 1/2.
Yeah. And that ends up being minus 5 sine of 1 plus t to the 1/2 divided by t to the 1/2. Now, if you put 1 for t in this second derivative, you get what its acceleration, x's acceleration, and you get y's acceleration.
Right.
The part I'm not positive on is what they mean by acceleration vector.
Okay.
Is that something different? In other words, is this the velocity vector?
Yeah. So, yes, it's the velocity vector if you put x prime, comma, y prime of t, like as a point.
Uh-huh.
That's how they're showing the vectors. So I think the acceleration vector of the rover at time t equals 1 would be a point. That's what I've noticed. The vector are two
Well,
values.
at that point, yeah, it's going to be a number. What I got was that, well, hold on a second. This is even more confusing to me. They're talking about the acceleration vector, and then they want the speed of the rover at time 1. Well, I can come up with the speed of the rover. This is the velocity of the rover here. Speed is
Right.
merely the absolute value of velocity.
Well, the speed equation is the square root of dx dt squared plus dy dt squared. That's how they get the speed.
Okay.
But for the acceleration vector, our teacher's been having us write the vector as a coordinate point per se. I don't know if it really represents a coordinate point, but that's how he's been having us write it. So we find a value for x double prime of t, and then find a value for y double prime of t, and then write it as
As those 2 points.
yeah.
Okay,
That's
well,
what
that's easy enough to do. But evaluated at what point?
at
Because
1 at time t equals
speed,
1.
well, if find the speed of the rover at that, okay, so we're going to square that, we're going to square that, we're going to add them together, and then we're going to take the square root of it, and then we're going to substitute 1 for t, and that's going to give us our answer?
That'll give us the speed, yes.
That'll give you the speed. Okay.
And then the acceleration is just completely different. I think it's just two-part equation, two-part problem. I don't think it.
Yeah, I find it curious that this is all together. It's like we're going to need this acceleration vector to figure out the speed of the rover at time equal 1. That's what's confusing to me because it doesn't seem like we do need it. In other words,
I don't.
speed, I agree, that's speed, okay, but we already have dx dt, that's dx dt, we have dy dt.
Right.
So we don't need the acceleration vector for this finding the speed of the rover at t equal 1, unless
Right.
I'm completely misunderstanding it.
I don't know why they're asking. I don't think you're misunderstanding. I don't think you're misunderstanding it at all.
Okay.
I think the test maker just wanted you to find both. That's
Okay.
We saw a problem like this in class too,
Uh-huh.
and we didn't like the acceleration vector. We didn't need it for the speed of the rover.
Okay. So what do you suggest?
Usually it's like two
Acceleration
different parts.
vector, should we plug in 1 into these 2 equations up there and come up with a point?
Yeah.
Okay, well, you can do it as easy as me. That's going to be a calculator problem. But if 1 is what we have to plug in, then so our point is going to be an x and a y coordinate. See, to me, that says position.
Right.
Not acceleration. Here's my take on it, okay? Clearly, the point starts right there, okay? And then it goes up, and they tell us that's the starting point, 6 comma 5. Then it's going in this direction. So clearly the y is going to the left, so it's going to have a negative acceleration or a negative velocity. I meant the x, not the y. But the y is also going down, so it also is going to have a negative velocity.
Okay.
Until you get to that point right there, and then the x turns around and starts going the other direction. So
Right.
the vector would maybe be the tangent line I don't know. No, the acceleration vector has to be the second derivative of those first two derivatives. It's just I'm not sure that that's an answer for an acceleration vector. Sounds like it's not. Maybe the best thing to do would be to table this part of this problem until next time. And I tell you what would be really helpful on a problem like this is if you have an example that your teacher has given you, bring it in, because I can't find an example of this in the book.
Okay.
Okay.
I do have this.
Oddly enough, the equation for speed is the same equation as for arc length.
Right.
Which I'm puzzled by. But anyway,
Except doesn't arc length have an integral in front of it, though?
Yes, you're absolutely right.
I do have solutions for these problems if you would like me to send them to you as well.
I'm sorry, what?
I do have solutions with these problems that I can send to you when I send these.
That always will solve it. Yeah, that's the best thing. If you can do that in the future, let's do that. And if you have time today, let's come back to this one, to the first part of this one. And yeah, if you have the answer, I think I can figure out how they got it.
Okay.
But while I wasn't total failure on this. How about B?
B. Find the total distance that the rover travels over the time interval 0 is less than or equal to t is less than or equal to 1, from 0 to 1.
Can you give me the equation for that?
Well, total distance traveled, so we'd have to take the integral.
Right. It's arc length is what they're asking about.
Okay, so that is arc length?
Yeah. In other words, if you take your rover and follow it along that initial curve, the total distance traveled is going to be the length of that arc.
Okay.
Going from 0 to 1 second.
So whenever I see total distance traveled when I'm looking at parametric equations, should I just think arc length?
Arc length. And again, this is dx dt squared plus dy dt squared. And I do find that curious. No, I don't find it curious. That's the speed, and the integral of speed is position.
Yeah.
In other words, the integral, that's speed, which is not exactly equal to velocity, but it's the absolute value of velocity. So if we integrate velocity, we get position.
Right.
Or in this case, distance traveled. This is easy enough to do. Number B, I didn't actually do it, but once you set it up, surely this is calculator?
Yes.
Because you're going to have some nasty integrals to integrate here.
It is calculator. He said, our teacher said that most parametric and polar free responses will be calculator.
Okay.
Unless you, unless it just says write the integral or something like that. If it says find, it will be calculator.
And I think I can handle C also. If we want the coordinate, the y coordinate at time equal 1, then we have to do what?
I'm not sure.
Well, position is the integral of what?
Speed?
Yes, or velocity.
Right, but how do I just find it for just the y coordinate?
Well, here's what we're going to do. We're going to take the integral of the dy dt, which is 10 cosine 1 plus root t dt. We're going to come up with an indefinite integral, but we have an initial condition. In other words, we're going to come up with an answer plus c. that
Okay.
something you can do on your calculator right now? Or not?
Just the integral from 0 to
Yeah,
1?
just the improper integral of 10 cosine parentheses 1 plus t to the 1/2 power in parentheses.
Do I have what should I put for the bounds of the integral?
Oh, you can't do indefinite integrals on that, can you? Let me see if
No.
I can do it on Wolfram alpha. I think I can.
Okay.
But that's going to be critical because we're going to use the initial condition of what the y coordinate is at t equals 0. And then we'll have the full function, and then we'll just plug in t equal 1, and we'll have our answer. So, let's see. Can't even find Wolfram alpha now. Okay. Probably I ought to start using Desmos. I got a feeling this might even be easier in Desmos. But I know I can do integral without it being definite of, what am I doing? 10 cosine 1 plus t raised to the 0.5. Let's see if it adds my dt. Yes, it did. Okay. So, this answer, and let me just do all my writing up here. Plus c, there's the plus the constant.
Mm-hmm.
That is our position function.
Okay.
Okay. And that will tell us, that's actually not our position function, it's the y position function.
Right.
Y is equal to that. Well, we know y is equal to 5 at time 0, correct?
Right.
So 5 equals 20 square root of 0 sine of 1 plus cosine of square root of 0, which means 1 plus c.
Okay.
Now that takes care of that term. And we're going to be able to solve for c. C is going to equal, is that 20 outside the whole thing? Yes, it is. So I can divide that. I get 1/4. 1/4 minus the cosine of 1, which is, what is the cosine of 1?
Cosine of 1, 0?
No, these are in radians. So that's like pi over 2. I don't know. If you're in radians and you look up cosine of 1, it'll tell you.
Okay. Cosine of 1. 0.54.
0.54?
Yes.
So C is equal to 0.25 minus 0.54 minus, we'll round it off to 0.29.
Yep.
So now we have our equation. Y equals 20 times root t sine of root t plus 1 plus cosine of root t plus 1 minus 0.29. Okay? So
And then we just
this is
put in
the
1.
exact, explicit position function for the y coordinate.
Okay.
In other words, if I were to plug in 0, I should get 5. Because I know that at time 0, the y coordinate is 5.
Right.
So if I plug in, what do they want to know it at 1?
Yes.
So what does this look like? It's going to be 20 times sine of 2 plus cosine of 2 minus 0.29.
Okay.
That should be the answer. Now, I don't know if you want to take the time to do that or not, because it would be worth, we can kind of get an idea of what the position of y is going to be by just tracing the thing. The problem is we don't know where t equal 1 is on that path. But we do know that the y coordinate is going down, I think, all the way, is it not?
The y coordinate is going down?
Yeah, I can't pull it up without erasing everything I've written here. But if you look at your original problem, the y coordinate does nothing but go down. The x coordinate goes left and then back right, but the y coordinate always goes down.
Right. I have a question, though.
Mm-hmm.
So why can't we take the integral from 0 to 1 of 10 cosine 1 plus root t and then add 5 to it? Because that's the initial y value.
Because the initial y value isn't c. In other words, we got c from doing an indefinite integral.
Right.
And then we have an initial condition that we know y is 5 when t is 0. So we plug in 5 for y. We plug in 0 for t. And that allows us to calculate what c is. And then that gives us our position function for y, top function.
Okay.
I could get a position function for x in exactly the same way. So if they're going to follow up this question with where is x at time 1, we would do it exactly the same way.
Okay.
All initial value, think of it as an initial value differential equation. Because that's what we have is a differential equation, and we know an initial value on it. So if we integrate it, we get the position function with a c,
right,
and then we can calculate c. That's the way most all of them go. So I'm going to go ahead and erase this. Is that okay?
Yeah, that's good.
Okay. And let's look back at our next question. The rover receives a signal at each point where the line tangent to its path has slope 1/2. At what times t does the rover receive the signal? Well, that should be relatively easy.
Do we set dx dt equal to 1/2?
Yeah. Which is find, hold on a second, the line tangent to the path. That's dy dx.
Oh, so that would be dx dt. No, dy dt over dx dt equals dy dx.
Yes, that's what's equal to 1/2.
And then we have to find from 0 to 2 where it equals to 1/2.
Right.
Where
In other words, here's our we're going to put, hold on one second. think I can do it pretty quick here. At least set it up. So we're going to take dy dt. We're going to divide it by dx dt. And we're going to set that equal to 1/2 with our domain being 0 to 2. Now, if we look at that, first of all, is that a solvable equation? Yeah, I'm not sure I know how to solve it, but Wolfram Alpha would solve this for us, and your calculator would also. I guess, I don't know. Do you know how to solve an equation like this in your calculator? You have the Inspire or the TI-84? John, did I lose audio?
Sorry.
Oh, that's
Sorry.
Okay. Do you have
the mute was on for some reason.
Do you know how to solve this?
I think I do. I'm gonna try it right now, and I have the TI-84 plus CE, so it's got the LED screen and stuff, but I'm not sure.
Okay, the one way I know that's the easiest way to solve this is multiply both sides by the cross multiply. So you end up with this. Put that in as y sub 1.
Okay.
And it's got to be equal to minus 12. Put that in as y sub 2. And wherever they cross, that's your t.
Okay.
In other words, this function might look something like a cosine function. The second, this is y sub 1, this is y sub 2. The second might be like that. Your answers are those 2 points. Well, depending on where the t scale is.
Okay.
In other words, when you put these in, you'll just get not a parametric equation, but in fact, you could put these in as x, if you like, and you'll get a value of x where they cross, and that's what they're looking for. Is what do they want? Hold on a second. Yeah, they want the points. Did they say whether they want the? No, they want the times where it gets the signal, which is exactly what you'll be solving for. So whatever time you get, if you get a quadratic and you get 2 different times, well, then there might be 2 different times. It looks to me like there would be at least the slope has to be a half, right?
Right.
There's a point where the slope looks to be a half. There's another point where maybe it's a half. Maybe this is not ever a half. Maybe that's always greater than a half. So the only answer would be this point here. Believe it or not, that's going to be a positive time. I know it looks negative, but it's a negative x coordinate.
Right.
Time is counting, time 0 is right there, and everywhere else time is positive until you get to the bottom right there. That's time equal 2, I presume.
Right.
So it goes like this, you know.
Right.
And to me, it looks like the only place where that slope is going to be a half is probably right there.
Right.
Down below, it looks a little steeper.
Right.
Hard to tell.
I figured out how to do it in the calculator too.
Okay, cool.
And it's in the numeric solver.
I'm sorry, what?
It's in the numeric solver. And you just put in the equations.
Oh,
If another student's
and
asking
it'll
you.
solve it. You have a problem. You have an equation solver in that.
Yeah, the equation solver, and then but you got to make sure. The only thing with the equation solver is what I have to remember and what you have to remember, just like if you have another student asking, is the bounds are from like negative infinity to positive infinity. So your guess has to be like in the middle of the bounds that you're trying to find the answer in.
Okay.
So like my guess was 1 because the equation was from 0 to 2, and I got 1.07 too.
Okay.
Which is the right answer.
Okay. Oh, good.
So.
Okay. Let's see. That was the last question.
Yep.
So let's see. We don't really have any more time, but I was curious as to what the answer was to A. Find the acceleration vector. If you have the answers in front of you.
Yeah, I have the answer to A. The answer to A was, so it was interesting. So the vector, the way they wrote it, was like a triangle on one side, like a sideways caret thing, and then 19.975 comma negative 4.546, and then another caret thing, like sideways, like a greater than or equal to sign kind of thing.
Were you talking about on top like that?
No, on the side, but like the opening is facing the number.
Oh, like this. Oh, that's vector terminology. What was
Yeah,
the
and they had
second
it on
number?
both sides. And then the other number was negative 4.546, which is what I got in my calculator. So.
Yeah, these signs mean we're talking about a vector, I think.
Okay, I didn't know that. I just wrote it as a point. I got the same numbers, but I didn't know you needed the triangle things.
Okay. So this was the answer. And is that what you
Yeah.
get when you plug in t into the second derivatives?
Yeah, when I plugged in 1 to each of the second derivatives on my calculator, that's what I got.
That was the x coordinate and that was the y coordinate?
Yeah, that was the
Okay,
x
well,
double prime.
that's fairly straightforward. Okay. So you
Yeah, and
plug in
then
the speed. I'm still a little puzzled about that, but
the speed.
yeah, because the speed is the first derivative. And yet the acceleration vector, you'd think that would be talking about the second derivative, which we are, but I don't understand why we plug in the speed. Oh, no.
They just have it written as 2 answers.
I'm going to have to think about this one for a while. But anyway, I'll let you go for now.
Okay, thank you so much.
On Friday, if you have answers, go ahead. And let me add one additional thing. Are these problems you're getting specifically from your teacher, or are you just pulling them out of a AP practice calc ABC book?
He made the packet for us.
Okay, because I do have on my computer 2 practice tests for the BC exam.
Okay,
So
yeah,
if
we
you're
have
looking for problems to go over and your teacher hasn't given you any, I got tons.
Okay, thank you.
All right. John, have a good day. Talk to you on Friday.
Okay, thank you.
Bye-bye.